All right, I just need to wait for my file to convert, and then here we go. Waiting. Here we go. All right, we are looking at compound events. And I already did the notes, so here we go with the practice. Look back at the opening question about locks in case you need to remember, but we're going to determine which password is less likely to be guessed. Password with 3 numbers or password with 3 capital letters. Well, our sample space for 3 numbers is 10 numbers times 10 numbers times 10 numbers. And, whoops, nope. And our sample space for, let me do this. There we go. And our sample space for 3 capital letters is 26 times 26 times 26. And so hopefully you would realize without doing the math that 26 times 26 times 26 is bigger than 10 times 10 times 10. But in case you can't, 10 times 10 times 10 is 1,000. And whoops. And 26 times 26 times 26 is 17,576. So a password with 3 capital letters is the better password system. All right, using a tree diagram to find the sample space and the total number of possible outcomes. Okay, so our sample space, we've got mini golf. I'm going to make that an M. Laser tag, make that an L. R, make that roller skating. All right, so we've got M, L, and R. And we've got times. And so we've got 1 to 3 and 6 to 8. So we could go, let's just call them first time and second time. So we can go the 1 to 3, or we can go the 6 to 8. Then here we can go 1 to 3 or 6 to 8. And here we can go 1 to 3 or 6 to 8. And so we can see we have 6 outcomes. Now the next one, use a tree diagram to find the sample space and the total number of possible outcomes. So we've got a keychain and a magnet. So we've got K and M. And then we have blue, green, red. And over here we've got blue, green, and red. Your friend finds the total number of ways that you can answer a quiz with 5 true-false questions. Is your friend correct? So our friend is not right. So the issue comes down to there's 2 possible outcomes, which is why he has the 2's there. However, he didn't use the fundamental counting principle because he's adding. So my friend should have added. No, multiplied, sorry. My friend shouldn't have added, he should have multiplied. Multiplied. I think I'm going to need a new nub of my pen. I think that's why it's freaking out there. We'll worry about that a little later on. All right, so down here, again, we're going to use the fundamental counting principle to find the total possible outcomes. So we've got, in battery, we've got 1, 2, 3, 4. And in color, we've got 1, 2, 3, 4, 5. And so we're going to go 4 times 5, which is 20. Meals over here, we've got 1, 2, 3. Over here, we've got 1, 2, 3, 4. And down here, we've got 1, 2, 3. So that's 3 times 4 times 3, which is 36. You randomly choose one of the marbles. Without replacing the first marble, you choose the second marble. Name 2 ways you can find the total number of possible outcomes. Well, you could make a tree diagram. Oops. Or you could use the fundamental counting principle. So find the total number of possible outcomes. Using the fundamental counting principle, I'll start backwards. You start off with 4 marbles, and then you'll have 3 marbles, so there's 12 possible outcomes. Using a diagram, it would start off with G, B, R, Y, and then afterwards you go R, B, Y, go G, R, Y, you go G, B, Y, and you could go G, B, R. And so you can see here that again, you'd have still 12 possible outcomes. You spin the spinner and flip a coin, find the probability of the compound event. Spinning a 6, well, there are no 6s on here. So probability of doing any of that is 0. Spinning a prime number and not flipping heads. So spinning a prime number, there's 1, 2, 3 prime numbers out of the 5. And then flipping a coin and getting heads, or sorry, yeah, getting tails is probability of that is 1 out of 2. So we could say it's 3/10. Now, I just used the fundamental counting principle for that. Again, if you don't want to, you go 2, 3, 5, and then heads, tails, heads. Actually, I suppose I need 1. Hold on. Sorry. I need to show the whole tree. I forgot about that. I'm so used to skipping ahead with some of this stuff. The whole tree. The whole tree would be 1, 2, 3, 4, 5, and then heads, tails, heads, tails, heads, tails, heads, tails, heads, tails. There's my sample space. And if I look at this then, I want the ones that are prime and not flipping heads. So that's this one, and this one. And so we can see that that's 3 out of 10 possible ways of dealing with that. Okay, you spin the spinner, flip a coin, then spin the spinner again. Find the probability of the compound event. So spinning the spinner would be 1, 2, 3. Flipping a coin is heads, tails, heads, tails, heads, tails. And then spinning the spinner again is 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So we want to not spin a 1. So that starts us off in the 2 and the 3 column. We want to, oh, by the way, the sample space size is 3 times 2 times 3, which gives us 6 is 18. So there's 18 possible outcomes. Now of those, we want to start here and here. And then we want to continue on flipping tails, so here and here. And then spinning an even number, that's here and here. So it looks like there's only 3 outcomes. Sorry, there's only 2 outcomes that match that. So we're looking at 2 out of 18, which is 1/9, which means there's an 11.1% probability of that compound event. You forget the last 2 digits of your cell phone password. What's the probability that you randomly choose the correct digits? Well, there's 10 possible digits, and you've got to do that twice, so 100. And you've got to get them in the right order, so that's 1 out of 100, which means there's a 1% chance of you randomly choosing the correct digits. Suppose you remember that both digits are even. How does that change the probability? Well, now you've improved your odds because you know that there's 100 digits. Well, I think the better way to do this would be to say you now have a 1 in 5 chance times a 1 in 5 chance. I think this happened last year, and it means I need to change my pen. And so that gives you 1 in 25. And so 1 divided by 25, and that gives you a 4% chance of getting it correct then. A train has 1 engine and 6 train cars. Find the total number of ways an engineer can arrange the train. The engine must be first, so we're just arranging 6 train cars. So the first train car could be 6, second train car, well, all right, first train car, there's 6 possibilities. Second train car, there's 5 possibilities. Third train car, there's 4 possibilities. Then we have 3 possibilities, then we have 2 possibilities, then we have 1 possibility. So 6 times 5 times 4 times 3 times 2 times 1 means that there's 720 possible ways of arranging that train. You have been assigned a 9-digit identification number. And should you use the counting principle or a tree diagram to find the total number of possible identification numbers? You should use the FCP. A tree will be too large. You do not want to make a tree out of this. So how many identification numbers are possible? Well, with 9 digits, we're doing 10 times 10 times 10 times 10 times 10 times 10 times 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. And so that means that we're looking at 1 with 1, 2, 3, 4, 5, 6, 7, 8, 9. There's that many. That's thousands, millions, billions. There's 1 billion possible identification numbers then. A social media account password includes a number from 0 to 9, an uppercase letter and a lowercase letter, and a special character in that order. There are this many possible password combinations. How many special characters are there? Okay, so 0 to 9, that's 10 numbers. Uppercase letters, that's 26 letters. Lowercase letters, there's 26. So what we're going to do is we're going to work backwards. We're going to go 223,080, and we're going to divide by 10, and then we're going to divide by 26, and then we're going to divide by 26 again. And that'll give us the number of special characters. So we have 223,080 divided by 10 divided by 26 divided by 26. There are 33 special characters. What's the probability of guessing the account password if you know the number and uppercase but forget the rest? So you've got the first 2. It's the last 2 that you're not certain on. Well, with the lowercase times the 33 for the special characters, that was 26 times 33. That gives us 858 possible combinations. So you have a probability of 1 out of 858. 1 divided by 858 gives you this times 100, gives you a 0.12% chance of guessing it right. From a group of scientists, an environmental committee of 3 is selected. How many different committees are possible? So we've got 5 scientists, an environmental committee is picked. So we're going, at first we have 5 scientists, then we have 4 scientists, then we have 3 scientists. And so 5 times 4 times 3, we could get 60 different committees. And then to remind you how to do these guys here, use the bar graph to find the experimental probability of the event. We've got 13, 6, 15, 17, 19, and 20. So we're going to add all those up to find our total possible outcomes. 13 plus 16 plus 15 plus 17 plus 19 plus 20. So there's 100 possible outcomes. Out of that, we're doing, we want number less than or equal to 4. So we want these 4 right here. So we're looking at 13 plus 16 plus 15 plus 17, which gives us 61. So we're looking at 61% is my experimental probability. And the number 17 is just -6 times -2. Two numbers when multiplied together that are both negative will become a positive, and so 6 times 2 is positive 12. The last 2 problems are, well, the last 7 here are on you. This right here is the purple one. I know it didn't show up on your sheet. I will tell you this in class, but some of you will still not listen to me. All right, thank you.